This is, again, just a reminder, this is week 8 of the semester, but we're going to cover week 7 content. So we're going to be talking about transformers today and sizing some. So this is our MCC and office transformer sizing week. Everything that you're going to need is your one-line drawing, your design notebook, something to take some notes with. If you also want to open up the bulletin book, there's going to be a couple of pages that I just referenced in there real quick. But if you want to pull that up as well, that should be everything for today. Alright, so we're going to start out talking about our MCC transformer size. So, what that is specifically, of course, we have our MCCs. And our MCCs are operating on what voltage?
480.
Very good, 480, right? So that's what's energizing all of our motors. And really that's more like 480 or 277 volt. And of course that's 3-phase. So that's what our MCCs are fed with. Now, kind of going back here a couple weeks ago, whenever I said we were talking about our shop receptacles, and I said that those MCCs were going to share that receptacle load in the shop, okay? And if you also remember how we had this section 6 in those MCCs were X'd off, that's because the equipment we're going to put in there is going to hold our shop receptacles. Well, we kind of come over here on this little, somewhat one line I'm drawing for you. Our receptacles have what voltage on them?
120.
120, right? It's just 120 single phase. So we got to get from here to here in terms of our voltage. So we're going to use a couple of components to do that. The first one that ties into this MCC bus is going to be this transformer that we size. So we're going to size a transformer that goes from 480, 277 down to 208, 120. You might ask, well, why that? Well, because this transformer is then going to feed what we're also going to install today, but that is a panel, and we're going to call that shop receptacle panel, number whatever. Each MCC is going to have one. And of course, this is going to have our 208, 120 available in here, and also be a 3-phase panel. But we could just take a single phase of that and run out to our receptacles. Like I said, this is going to be in every single MCC. This is the exact same process. So this is going on inside of section 6 there. So we could say, all right, well, each MCC has X amount of receptacle circuits being fed out of it. So we could size the transformer specifically to that load. You could do it that way. However, let's just say you only had a handful of receptacle circuits being fed out of this MCC, so you size your transformer according to that. Well, this panel, there's only one panel that we're installing. So if you ever come back in and put more receptacle circuits, you would potentially have to change out this transformer. So rather than basing it off of the number of receptacle circuits that you actually have, we're going to look at what is the maximum capacity that this panel can handle. And we're going to size our transformer to handle this capacity, not our actual number. Does that make sense? So, the first thing we'll look at here is in our bulletin book. We actually looked at this page. This is page 7, by the way, if you want to follow along on your screen. But we looked at this bulletin 2193 LE a couple weeks ago whenever we did our lighting circuit in the shop. It's the exact same panel that we're using to house all of our receptacle panels. So we chose this one down here at the bottom. It says that it can hold 15 circuits here, but by the time you lay it out, that's where you get that 16 circuits. So again, kind of going back a few weeks when I told you all shop receptacles, make sure you only had 16 arrows pointing back to each MCC. So if this panel can handle 16 circuits, well, what's the maximum load in watts that those receptacle circuits can have for our project? You put 4 outer wall receptacles or you put 2 machine mounted receptacles together, what's the wattage on that you can't exceed? 1600, right? So we'll just size, again, everything for the maximum. So we'll take 16 circuits, which is the max number of circuits that this panel can hold. We're gonna multiply it by 1600 watts, which is the maximum a circuit can have. So when you do 16 times 1600, what do you calculate? So we can just say 25.6 kilowatts? Okay. So that's the maximum potential kilowatt load that this transformer will see. However, what units are transformers listed in?
KVA.
KVA. Well, are KW and KVA the same thing?
Listen.
So how would you convert KW to KVA? What's one thing that we're missing there to do that? What do we need to know?
Average.
Not necessarily. What'd you say? Power factor, right? So if we had our power factor, we could convert our kilowatts to KVA. However though, does anybody want to take a guess on what our power factor is for this project? Which is also known as what? Unity, right? So, we looked at this formula a few weeks ago. If we take this 3-phase equation, power 3-phase is equal to square root of 3 times what? Do what?
Would be 25.2.
Now, we're not gonna fill in numbers at the moment, but what would come next? What would be the next variable in this? No, close, that's a different formula though. That's for our circular mills. We use this formula, I believe when we did our AC unit stuff. But you got your voltage in the line times what? Y'all have seen this formula before too.
Your eye line.
There you go, I line. There is a variation with phase phase here. There is a variation with your phase values. It's very similar to this. But current in our line, and the last little portion is the power factor, but what's the formula for power factor? Give you a hint. Part of it is a function on your calculator, and then the other part you need something else. Your triangle. Power triangle. There you go, cosine theta. So, another reason I like this formula here but power is expressed in what units?
Watts.
Watts, right? So we got kW is equal to, and then if you take volts and amps and put them together, there you go, you got volt amps, right? So this portion here is our kVA. And then lastly, cosine of theta, that's our power factor, right? So mathematically, we can prove that if we have a unity power factor, doesn't kVA and kW become the same thing? Yes, right? And again, if we kind of remember our little triangle over here, our little power triangle, you got your kilowatts over here on the bottom, you would have your kVARs going this direction, for example, and then you would have your hypotenuse here as your kVA. And remember, this is that theta angle. Well, if your angle is flat, well, isn't kVA and kW laying on top of each other? So they're the same thing. So, with our power factor being unity for our project, so I'm a nice guy, we can mathematically prove, all right, well, kilowatts and kVA are the same thing. Now, are you gonna have a unity power factor out in the field? Probably not, no. I would say that would be a very rare occurrence. You might have some stuff pretty close to it, but I don't think I've ever seen a perfect 1.0 power factor before. But again, since this is our project and we're a school, we can kind of step away and say, you know what, we're gonna just say it's a unity power factor, mostly for simplicity reasons. So with that kind of being determined, now this 25.6, that's also kind of the amount of kVA that we need to size our transformer. So, kind of going back over here to our bulletin book, if you scroll down to the next page, page 8, you have this bulletin 2196, and this is transformers that are designed to be inserted into this MCC. So we have several options here. We can get just a single phase 120 volt secondary. Well, that's not really exactly what we need. Same or very similar single phase 240 120, not really what we need. But then they do offer a 3-phase, 208 120 transformer, which is exactly what we need. So this list over here on the left hand side, that's our available transformer sizes. So what size do y'all think we need here? 30. That's what I would go with, is our 30 kVA. The other important piece of information that we'll get off of this is if we kind of follow this out, this last item over here, that 3.0, that's referring to its space factor. So I will make a note of that over here. Anybody have any questions on how to size that MCC transformer?
So you're only gonna have one of those, right?
You're gonna have 6 of those.
6 of those, and they're all gonna be 30?
Right.
Okay.
Yep.
All
So
those-
each MCC is sharing those loader receptacles, right? So each MCC is gonna have to have a transformer, a panel, and then the receptacles that it's serving. Everybody's good with that sizing? Okay. So probably some good news you'll like to hear, but this math right here that we just did, there's not a sheet in the design notebook to show this work. Okay, the reason for that is because this is a group activity here, right? Everybody has the same panel, everybody has the same same MCC. So eventually y'all are all gonna land up at the same transformer size, right? So this is just a group activity. But rather than just saying, oh yeah, your transformer is gonna be 30 kVA, we walked through why and how that transformer is gonna be a 30 kVA. So there's not necessarily a page to show your calculations work. However, there is the drawing portion of that. And that we will cover real quick. So on the one line, so again, on your MCC elevation here, you should still have that section 6 blocked off. Of course, your MCC should be filled in. Mine's not, because I don't save that work. But in section 6, this is now where we're going to install both the transformer and the panel in there. So we can go ahead and kind of get rid of these. Get rid of these cross marks on there. Now, as far as the transformer and the panel goes, we know the transformer is going to take up 3.0 space factor, and the other thing which is considerable in size as well, but the other thing we have to focus on is whenever y'all are in Transformers Lab, I think it was like maybe the second or third week in there, y'all remember dealing with those control transformers, probably about yay big. They were real small transformers,
Yeah.
like 0.25 volt amps, something like that. But if y'all remember, those things had some weight behind them, right? But they weren't very large. Well, we're going all the way up to a 30 kVA, so it's gonna be pretty heavy. So where we put this in our MCC section kind of matters, because these MCCs are about the same size as the ones in your machines class. So we don't want to take this 30 kVA transformer and say, let's put it at the very top, because then that's going to be a lot of weight suspended up in the air that we have to install into the MCC. So it just makes it, one, more difficult for us, and two, a little bit more unsafe. So we're going to try to keep that weight at the bottom. So we're going to put our transformer in the bottom portion of that section 6. So since it's 3 space factor, very similar thing, we're just gonna visually represent that. So I'm just gonna delete those 3 lines right there. So now I'm visually representing that 3.0 space factor. And we're just gonna put some text in there. And we're just gonna say 30 kVA. And we'll say that it's a transformer. And then we're gonna list out the voltages. So you're gonna start with primary phase to phase, which is 480, / primary phase to ground, which is 277, dash to indicate that we're done talking about primary and then switching over to the secondary. Very same thing, secondary phase to phase, which is 208, / its phase to ground, which is 120 volt. And then we'll also list it as a 3-phase transformer on here. So that's our transformer. Now we have to install that panel. Well, if I go back to my bulletin book here, scroll up to that panel page, you'll notice our panel takes up 2.0 space factor. So we'll put that directly above our transformer. So now I'm visually representing that 2.0 space factor, and then we're gonna put some text in there. So we'll call this our shop receptacle panels. And I'm just gonna put a number there temporarily, but again, you don't wanna just have shop receptacle panel, right? Cause you're gonna put this in every single MCC section 6. So if you had 6 panels and they were all called shop receptacle panel, that would be a little confusing, right? So since I'm in MCC 1, it would just make sense to me to label this as shop receptacle panel 1, right? And then when you go to MCC 2, that would be shop receptacle panel 2, and so on. So we will identify those panels. We'll list the voltage that's present in them. So this panel has 208, 120 in it, and that is 3-phase. And then we're gonna list our number of circuits. So I don't have an actual number, but for example, if you had, let's just say 12 receptacles out of there, then you're gonna, or 12 receptacle circuits, I should rather say, then you're gonna put 12 circuits. If you had 8 circuits, then you're gonna put 8, or however many you have being fed out of that specific panel, that's the number that you're gonna fill in there. And so by the time we install the transformer and the panel, that pretty much occupies the entirety of section 6, except up at the very top, we do have that 1.0 spare left over. So just like any other extra space in our elevation drawing, we're gonna label that as a spare. So kind of once you do one, you can take that setup and copy and paste it into all your other section 6s, just changing the panel number and how many circuits you have out of each panel.
Really, the only thing that's gonna be changing from each MCC is the number of circuits.
The
that's
number-
stated on that,
The number of circuits and the panel number.
and the panel number,
Yeah. Yeah, the transformer's gonna stay the same, it's just the panel number and the number of circuits.
How did you do the phase symbol?
So that, I will give you a little hint on that. So you have to be in the text editor, so that little text box. But if you come up here about 3/4 of the way down, you'll see that @ symbol. And if you hit that drop down menu, probably about 1/4 of the way down, you'll see where it says electrical phase. If you just click that, it'll drop that phi symbol in there.
Thank you.
Yep. So everybody's good with the MCC transformers? Okay. So like I said, this is the only kind of place here that we're gonna be showing our work. It's just right here on this elevation drawing. You don't have to do anything to the shop drawing, it's just taking place on this elevation drawing here. Like I said, there's no calculations on the design notebook for that. Alright, so now we're gonna kind of switch gears here a little bit, and we're gonna talk about our office transformer. So for our office, we have 2 panels. We have our office lighting panel and our office receptacle panel in there. What's another load in our office?
the air conditioning.
Our air conditioner. So if y'all recall from back from week 2, we actually fed that AC unit out of our ORP. So I'll kind of draw it as an extension over here. So both of these panels, both our lighting and our receptacle panel, both of these are 208, 120 volt, 3-phase. Right? And of course our AC unit over here is running just on the 208 portion. But how these panels get fed? Well, kind of leading into a little bit of main feeders, but all the wires that are gonna be coming in here to feed our MCCs, we're gonna have one that comes over here and feeds our office area. Well, kind of similar deal. If our main feeder is coming in over here at 480, 277, and we got 208, 120 here, then we're gonna have a transformer to step that voltage down. And it can come over here, then it can feed our panels. So, it's gonna be a similar sizing process to what we just talked about. So we're gonna kind of break this up into a few steps. But we're gonna size kind of each three of our loads here, starting with our office receptacle panel. So you're gonna go back to your office receptacle wire sizing page and you're gonna say, okay, how many circuits do I have? I'm just gonna make up a number, but let's just say I had 60 circuits of receptacles in my office. Well, if I got a total of 60 circuits, the first thing I'm going to do is I'm going to subtract 1 from it. Why? Because this AC is part of that number whenever you look at your page there. Our AC, that's going to be a separate calculation in this process here. It's not a true receptacle circuit. So we're going to take 1 circuit, and we're going to subtract it from it. So then that would leave me with a total of 59 circuits. So very similar process. We're going to have 59 circuits in this example. Well, what's the maximum load of our receptacle circuits in the office? In terms of watts?
200?
Not 200. If you tie 4 receptacles together in the office, what's that maximum wattage?
Wasn't it like 1,200 or something?
400?
That's 400 per receptacle.
Well, so it's for the amount on the loop, right?
1,600, right? You'll notice that as a theme across the project. So it's a very similar process. We'll take 59 circuits and we'll take 1,600 watts for the maximum wattage on there. And even if all your receptacle circuits don't have 4 receptacles on them in the office, that's fine. We'll chalk that up to future expansion. So if you had a receptacle that only had 2 receptacles on it, for example, well, we're gonna say, well, we might come back in the future and add 2 more to that same circuit. So we're just gonna do everything at 1,600 watts. So we take 59, multiply it by 1,600. I get 94.4 kilowatts. Now the only little thing that we're going to add and do a little bit different here is we're going to show any continuous and non-continuous loads. So our receptacles, are they considered continuous or non-continuous? Typically not. I know you can make the argument and say, well, some receptacles are, like in here, all of our computers plug up to receptacles and I'm in here lecturing for 3 hours or more, right? But generally, receptacles are considered a non-continuous load. So we're going to show that by taking our kilowatts that we calculated, so in this example, 94.4, and we're going to multiply it by 100%. That does not change our answer any, but it's showing that this is a non-continuous load. That's our receptacle panels load kind of taken care of. We're going to do a very similar process for our lighting panel. So let's just say, for example, you have 30 lighting circuits in the office. Well, guess what the maximum wattage is for the lighting circuits in the office is?
16,000.
1600, right? So we'll have 30 circuits in this example times 1600 watts. And when I do that calculation, I get 48 kilowatts. And we'll ask ourselves the same thing. Is these lights, are they continuous or non-continuous?
They're continuous.
So lighting loads are generally considered a continuous load. So even street lights at the utility company are considered continuous there, right? So you walk into a building, or street lights at night, they're running for 3 hours or longer most of the time. So we're gonna show that by taking 48 kilowatts times 125%. Very similar to our motor circuits there for continuous load. And that will change our answer. And I get exactly 60 kilowatts. So that kind of takes care of our lighting load. So the last thing to calculate here is our air conditioner. And this is where we're going to use that three-phase equation. So we're going to have power three-phase is equal to square root of 3. And we know that our voltage is 208. That's our line voltage, phase-to-phase value. And then does anybody happen to remember what the current is that we use or have been using besides our AC? Anybody happen to remember that? So we've been using 80 amps on the AC. Again, that's the maximum breaker size allowed for the air conditioner. Is the air conditioner actually going to be drawing 80 amps all the time? No, but we're not going to deep dive off into what it's actually going to be drawing all the time. We're just going to size it based off that max breaker size. So we'll plug in 80 amps for our line current. And then that cosine of theta, that's our power factor, but if it's 1.0, that's really not going to really change our answer any, right? But if you plug in your calculator, square root of 3 times 208 times 80, because this is another kind of group activity here, what do you calculate? Yeah, I think it's like what, 28.82?
Yeah.
I think it's like mirrored of each other.
Yeah.
So 28.82 kilowatts. Again, that's kind of a group activity because we all have the exact same air conditioner in the office, right? So, we're going to take this 28.82, and of course I'm just making up some numbers here, but we're going to also take the 60 kilowatt and this 94.4 kilowatts, and we're going to add those together. So that's kind of our fourth step here. Power always adds, right? And when I total that up, I get 183.22 kilowatts. So, what I just wrote up there in red, I would write that down, take a picture of it, something, because that's not listed on Canvas or on the bulletin book. Yeah,
So, for the ORP and the OLP, I know that you said that we, 60 circuits and 30, circuits, those are just random numbers that you made, right?
correct. So you're gonna substitute in your values.
Your values, okay, alright,
Yeah.
appreciate it.
Yes.
What is the word after transform,
Yes.
what are we getting with S?
Oh, sizes.
Oh, okay.
Yeah. Yeah, I didn't know my handwriting was that bad. Yeah, that says sizes up there. But yeah, up there in the red though, like I said, I would write those numbers down somewhere, cause they're not listed in Canvas or in the bulletin book, unfortunately, so write those down, take a picture of it, do something. But that's gonna be our available transformer sizes to us for the office. So based on our calculation here, what size transformer do you think that we need? 225, and these are all KVA values up there, I'm just not writing KVA after all of them. But I would agree with that, so this would translate to a 225 KVA. So, as Gavin kind of said, I just did this as an example here, but you're gonna still do the exact same process. The only thing that you're going to change is how many circuits you actually have in your office. So those two values there are the only thing that you're gonna change. So once you change that out, you'll still follow the exact same process. Step 3 here, our air conditioner unit, that's the same for everybody. Like I said, that's kind of a group activity because we all have the same size AC, but your number of circuits will change. So you can plug in your numbers, do the same process, add them up, and then pick your transformer size. So with the office transformer, it's kind of vice versa work of what we did for our MCC. So there's not a drawing that we're going to represent the size at this moment in time. However, there is a page of calculations in your notebook. So probably about halfway through or so, you'll come across a cover page that says office transformer sizing. The page right behind that says it again, office transformer sizing, but it's blank. So this is where you need to show these steps, where you're taking your ORP load, calculating it, same thing with the OLP, the AC unit, adding them up, getting your total kilowatts, and then selecting a transformer size. So basically this math that we just did right here, you need to take that and you need to put it on this sheet. So don't just say like ORP is equal to 94.4, for example, or OLP is equal to 60K, right? No, show your work on this entire process, show them what you calculate, and like I said, show them where you pick what transformer size you need there.
Do we have to show the work for the AC?
Yes, yep. So even though the AC is a group activity, still show, hey, here's my formula, plug it in my values, this is what I calculate for the AC. Yep. So even though that's a group activity, still show that process.
For the shock receptacle panels, you don't include the power circuits?
No, those are apples and oranges, two different things,
Yes.
right? So, the receptacles, circuits is obviously feeding our receptacles with this 120 volts here. The power circuits, that's all those buckets that we had to draw in like week 3 with all the space factors, right? So that's gonna kind of be in the other sections, and this is gonna be a 480 line coming out here to feed your machines.
Gotcha.
Right, so this would be 480 volts coming out this way to our machines. But for us to send this 120 out to those receptacles, we kinda have to do this process here. Right, so like I said, those are apples and oranges there.
You say the best way to do it is just basically exactly what you did, just copy and paste it and change your values around
For what?
for, recording the, sizing.
The office transformer? Yeah, you'll do this exact same process.
Yeah.
Exact same process. The only thing, like I said, you're changing is your number of circuits.
Okay.
That's it. And like I said, for those number of circuits, you're just gonna come back to those wire sizing pages. So like RC office, right? You're gonna go down there, you're gonna look, you're gonna say, oh, I had 60 circuits or however many circuits in there, right? That's probably a little high on both of those, but that's okay. You'll probably have less than what I set up here, so. And then you'll do the same thing for the lighting circuit too. So you'll just come over here to this page, you'll say lighting circuit in the office. Well, I had 20 circuits or 18 or however many that you got. Is everybody good with the office transformer sizing? Okay. Alright, so just to recap, there's nowhere to show the work or the math for our MCC transformer sizing, but this is where we went in and we drew in that transformer panel in the elevation drawing. Vice versa, over here with the office transformer, we are showing our calculations and our work for our math on the spreadsheets, but there's not gonna be a drawing associated with this at this moment in time. So everybody's good?
On the MCC wireway,
Mm-hmm.
I noticed that you have, it's a hashtag and then it says circuit. What is that like, what circuit do you fill in there? Do you?
So. The old Gen Zers. Hashtag wasn't always hashtag.
Pound sign.
Pound sign, which means just number.
Okay.
So, I just put that in there because I don't have, on my drawing, I don't have any receptacles or anything, because I don't save any of my work. So on that, right here, if you had, let's just say, 12 receptacle circuits being fed out of that MCC1, then you're gonna fill in hashtag with 12, right?
Okay.
Right? I just don't have any data to really fill that in, so it's kind of a variable, because you might have 12 receptacle circuits in your MCC1, but then Garrett over here might have 16, right? It just kind of depends on how y'all laid out y'all's shop.
Okay.
So I can't really say to put a defined number in there, because it's gonna be different for everybody.
Oh, okay, now I see what you mean, thank you.
Yeah. Making me feel old, man. What other questions y'all got? So everybody's good with both the transformer sizing this week? Okay. Like I said, don't forget on the MCC transformer stuff, that's in every single MCC section 6. Every single one of them, it's not just one. Alright, a couple of things real quick before I let y'all go. So, that was week 7 material. Again, this is physically week 8. Next week when we come in, we're gonna talk about conduit and panel schedules. Just a heads up, it's not difficult work by any means, but it is gonna be very tedious work. So a lot of number crunching, a lot of just sitting at the computer, just poking at the keyboard, okay? So, like I said, it's not hard, it's just a little time consuming, a little tedious, but nothing too terribly bad. So kind of be prepared for that. Also, again, this is kind of a lighter week. So just kind of reiterating from last week is if you're behind, hopefully you took last week as an opportunity to catch back up. If you didn't quite catch back up, I highly recommend you get caught back up again this week, right? So make sure you are where you're supposed to be at in the project. So again, my expectation is whenever we do something for the week, is you have until our next lab time to get that done. That's my expectation. So, like next Thursday when I see y'all, all of everything that we talked about today and all the other weeks should be 100% done, right? That's my expectation. So if you're doing that, you're doing really well in here, okay? So that's kind of your kind of guideline in here. So don't be falling behind. Just because you have some lighter weeks, that doesn't mean, oh, I don't have to do my design project this week, I can go play some Call of Duty. No, take the time, sit down, get it done first, then you can go play some Call of Duty or whatever, right? Also, with employer events, so this week, or today,